Okay, before we start our next module, which is really a review from 309 with a little bit of extra stuff, I want to cover something that you're about to encounter in lab before you get there and go, I do not know what I'm doing. So once you finish the basic electricity project, 4 I guess it is, you're going to get into creating some real circuits with some real motors and switches and various things. So it's kind of important to have some sort of idea how certain components work. And one of those components that seems to give people a lot of problems is, relays. Relays. So a relay is a component that allows a small amount of electricity to drive a very large amount of electricity. And for example, like on a standard small general aviation aircraft, you'll always have at least 2 of these type solenoids. So if you can imagine, let's see how an airplane would be drawn. So we have a battery, like my airplane, the battery's in the back of the aircraft, and this just goes down and there's a ground. And what I mean by that, it literally attaches to the side of the aircraft. So all the negative is the whole fuselage of the aircraft. And then there will be a very big wire that is going to come off of the aircraft and run towards the front of the aircraft, to the front of the aircraft. And this very large wire then will go up and run to, we'll say, the aircraft bus. And from the bus, all the loads go out. So what we'll do is we'll put a circuit breaker and another circuit breaker. I mean, they're literally screwed to the back of this metal strip right here. And then from the circuit breaker, I'll have a switch. At the top of the page. We'll do it this way, a switch that will control something, like maybe it's the landing light. I'm going to go out to the landing light, then ground somewhere. Follow so far? Okay, but we have to turn on this very large wire right here. I can't have it on all the time. Aircraft have a master switch. We turn everything off, the whole load of the aircraft goes off. So if I put a switch right here, it'd have to be a very large switch, kind of like a Frankenstein, big old knife switch, chunk, or something very large. If you really think about it, our light switches that control the lights up here, they're actually kind of big. And I want a very lightweight switch. So what ends up happening is you run a relay, and that relay would have a very large bar to it, a metal bar that does not quite make contact, but it will when it's drawn down. So what we do is we put a solenoid right here, solenoid. So that is a loop of wire. So in this case it'd be a solenoid, but the whole thing is going to be a relay. And when this is activated, I'll do it this way. When it's activated, it is going to create a magnetic pull that will pull down that bar to make contact and allow contact to go through. Well, that little tiny, that right there, just run it off of a switch. It runs back to the battery and has its own little power supply. Just a little tiny wire. Run it all the way up with a little tiny switch. Just a couple little, I don't want to say a couple amps, I don't think it is that much. So when this switch is closed, energizes this, pulls this down, and then you have this bar comes down, and then the bus is energized. And so there'll be one there, and there'll be another one that comes very similar right off of this wire right about this point. It's going to do another one. It's going to go off to the starter. So there'll be 2 right next to each other on a Cessna at least. So that is a relay. So again, to look at a relay, drawn out as you would see it. Let me see. Contact point, metal bar. So that's what the relay is going to look like. Yes?
So that smaller wire that you're talking about that has that switch, would you call that like a signal wire to the relay? What
Sure.
is that typically called?
I just call it the wire to the relay, but
Okay.
signal wire works good, yeah.
You said that's how you draw a relay right there? Or did
That's
you
how I
say-
draw one too.
Yeah, you're just saying that's what it looks like.
That's what it looks like, even holding it in your hand.
Both. You're saying.
Yeah, that's why I don't like you to use things like that and go, oh, that's a relay.
Right.
It's just like, sure it is. Looks like a firecracker with two ends on it.
So the schematic drawing should look.
Yeah, this is a proper schematic drawing. In fact, you may see it like this.
That kind of firecracker, you can get 2 bangs for your buck.
That's right. Light both ends. And you would have 4 attach points. 1, 2, 3, 4. 4 attach points. So what's going to attach to 1 and 2?
1 and 2 will be I would say in this case, your master battery switch.
Small wires. They're small control wires. So 1 would be maybe the power in and 2 would be the ground. Or 1 can be the power in and 2 can be the ground. If it's DC, it doesn't really matter.
Whatever generates a magnetic field.
Both of them do.
I'm just saying, like, you put either one.
Yeah, would it change the polarity if you have it in a certain way?
You have to rewind it and go the other way. And then 3 and 4 are going to be your big wires. So sometimes you're going to get a relay that's going to have more than 4 points on it. You just have to kind of figure out which way it goes, because sometimes it'll look like this.
It'll be printed on the relay, correct?
Somewhat. You could have it like that. Now what do we have?
It would be kind of similar
Double
to
double throw.
Double pole
Solenoid?
signal for a relay.
Okay, 5 and 6 would be called NC. Normally closed. So normally means, to me, I like to say it's without power on. Just at rest, how is it normally closed? Because some of the relays that we have that we hand out, they do have a normally closed position. Now this 1, 2, 3, 4, 5, I just threw those numbers up there. They're not going to correspond to what you have, but it's normally closed. With power off, that's what you're going to get. Normally closed, power off. And then when the power is on, this is going to come down here and go to 3 and 4, which are normally open. So with power on, 3 and 4 are going to pass through.
In the aviation world, where would you see a system like that?
I'm sure they're all over the place. I just can't think of one off the top of my head. I don't think I have one in my plane that does that, but maybe I do.
We use something like that for solenoid valves for hydraulics.
There you go. Yeah, I forgot there's some Q&A questions like that, and they have them in there.
Is the troubleshooting step, well, how would you troubleshoot if it's working or not? The way we did that was you just put a screwdriver to it, and if it sticks, then it's on or it's working, or
That works.
I don't know if there's a better way or a safer way to do it than just.
An ohmmeter? Or a voltmeter? See if you're getting voltage.
Lick it.
Lick it. Yeah. But anyway, I wanted you to make aware of that. And also switches, if it's spring loaded like this is, maybe it's spring loaded to the normally open. So anyway, that's a solenoid. And so you're going to be working with a lot of solenoids to do an upcoming project, and you have to understand how they are. And I tend to usually have to stop the lab class and go, okay, everybody, this is how it works. The more complicated ones that I've worked with before, I'll usually just I'll just go on the board in there and I'll write a little schematic for you real quick and just kind of show you how it is, because they're complicated and and I'm like, oh yeah, I remember now. But many of them we just have 4 points on it and they're wide open. You can just see 2 points going to a wrapped coil, and you can see 2 more points on a very large bar, and you're like, okay, well that makes sense, or it should. Which 2 are which? Cool.
Oh, cool.
Huh?
They're like open and
Yeah.
you can see everything.
Yeah,
Okay,
some are
so they're
open
not
and
gonna be
easy.
Like the mystery box.
Nah, and some of them are just a little mystery box that are.
At the 87, 30, 85, 84, I don't know what it is. Is that thing?
What?
No.
I'm not sure what you're saying.
Okay. Then maybe it's
Those
not.
sound like automotive relays.
Yeah, I was gonna say that's like the automotive. I don't know if that was. the same.
I don't know. I don't know where they came from or what they're doing. All right. Let's move on to electricity, which is really going to be more or less a review of week 2 of 309. So we should be able to go through it super quick. But because all this stuff is on a test, we're going to at least go over it. So, and I just see this new pin popped up right there. Let's see what happens. Atoms. Oh, that's just not going to work. Not if it's kind of printing like micro print there.
Do you have binoculars?
We just zoom way in. What? Yeah. We tried. Okay. Get rid of that one. Is there a way to get rid of that? Let's see if I can go. Yeah.
Might be able to do a different font size to it.
Think so?
I don't know. You'd hope.
I don't see any sort of drop down. See, this one has a drop down. This one does not have a drop
What
down.
about on the top right? There's like a little.
Who was that recommended you use this?
Oh,
I don't know, but I'm really actually liking it.
Was that Steven? Who?
No, it was someone else.
It was someone else?
Someone sat right over in this area.
Yeah.
Mhm.
It was Chris. I think it was Chris.
All right, but I do like it. Chris, they're blaming you. I like it. All right, atoms. Just got to get to the right, pen setting here to make me happy. Let's try that one. Atoms. All right, you tell me. Atom is considered to be the what?
Building block of all matter.
Right on. Atom, the atom. Now I've got atoms. Atoms are, or the atom is considered to be the most basic building block of all matter. Of all matter. Atoms consist of 3 subatomic particles. Consist of 3 subatomic particles. And that consists of, those particles are proton, neutron, and electron. All right, and let's see. We have the nucleus, which consists of, or it is the what? Where do you find the nucleus? It is in the center of the atom. And it contains what?
Proton and neutron.
Contains the proton, or protons and neutrons if there are more than one, which there usually are. Contains the protons and the neutrons. And let's see. Protons have a what kind of charge?
Positive.
Are you sure you hesitated? Positive charge. And therefore neutrons have a neutral charge. Why do protons have a positive charge? Who decided that?
Professor Proton.
Professor Proton. His name was Phil. Phil Proton. That isn't right. Anybody know? Oh, I believe it has something to do with. Is Benjamin Franklin involved in this one? I think he was.
I think he just he helped with like the discovery of electrons. I think was like the key.
Anyway, about that time, I think it was him. I could be wrong. It's not important. It's not on the test. But they rubbed wool on different things. They were rubbing materials on different things. And they, what's that? Satin. I think it was wool, and I forget what the other materials were offhand. But they would rub these things together and then notice that certain things happened to the wool, and then they just kind of said, well, that must be a positive charge. And so kind of had it backwards. One item gave off a bunch of electrons. If you give off the electrons, that becomes positive. And the other one collected a bunch of electrons, and that would become
Negative.
yeah. And I believe they had it backwards, and so but the theory was right. So anyway, inside of the atom, we have the protons and the neutrons, and they're down there inside the atom. And so protons have a positive charge, and neutrons have a neutral. Have to just put a little N for neutral. And for the most part, you have an equal number of protons and neutrons. So if I had 2 protons, I would have 2 neutrons. All right. And orbiting around said nucleus, we find electrons. There we go. They're orbiting around. And each orbit is called a shell. All right. So electrons. Talk about electrons. The electrons have a negative charge. Negative charge. And they move about the nucleus. They move about around the nucleus.
I have a question. Sometimes you use negative, sometimes you use neutral. I've always thought that they were the same. Are you doing that for any reason? Or?
Yeah, the neutrons are neutral. They have no charge whatsoever.
Ah, okay.
And the electrons have a negative charge. They actually are negative.
Okay,
So a
okay.
positive, neutral, negative.
Okay, gotcha.
In this case, that's very much so. All right, the number of protons, thus the number of electrons, can be determined by the periodic table of elements, which we're not getting into. Let's see. Yeah, I'll put that. The number of electrons. The number. Electrons. Let me see. What do I want to say? I'll just go with what I wrote. Number of protons, and thus the number of electrons, and thus the number of electrons can be determined by the periodic table of elements. Let me see. I used to have a copy of it in here, but I don't anymore, so we don't worry about it. Let's see. Arrangement of electrons cannot, and also, I'll just put and also the arrangement of electrons. Because if we go back to our 309 conversation and just a few minutes ago, we know that electrons, we need this drawing, are arranged in shells, if you will. They are arranged in shells. This is the Bohrs model, B-O-H-O-R-S model. It's not on the test, but just so you know, this is the Bohrs model. And we have, generally speaking, an equal number of neutrons and equals the number of electrons, and each one of these orbits is called a shell. And we can determine how many, the maximum, not how many, but the maximum number of electrons, which have a, what kind of charge? Negative charge. We can figure out how many electrons maximum per shell by the equation 2n squared, where n is the shell number. That is the shell number. And the outermost shell is called the valence shell. I'm going to write this stuff down. So, all right, arrangement of electrons. Let's see. I don't think I'm going to write this for you. The Schrodinger's model. The guy with the cat. You ever heard that? Schrodinger's cat. Same guy. more of a dog person, so. Model places the electrons in a probability cloud, meaning they can be found in a certain area, and they buzz about in this little area, and it's not important to us. Bohr's model uses a fixed orbit theory, which we will use because it's a more simplistic theory, and it works absolutely fine for the FAA, and that's actually what they have in their book, and so if we follow along, it makes sense. So the Bohr's model uses shells. So I don't know what number I'm at here. Electrons, let me see. Now we're still down here, so we'll call it 1, 2, 3. We will use Bohr's model, B-O-H-O-R's model. Uses a fixed orbit theory. Uses a fixed orbit theory. Like planets. Speaking of planets, it is my daughter's 17th birthday today, and which she likes planets and stuff, and so she wanted to go Saturn. You're supposed to be able to see the rings of Saturn these last weekend, and so I don't know if you ever heard of. It's called IHOP, not the pancake place, but Ice House Observation Point. So I took her up to IHOP 1. The moon was too bright; you couldn't see much anything. But anyway, I saw a really cool shooting star while we were sitting there. But yeah, there was nothing cool. It's kind of felt bad for her. It's a long drive. All right, we use this. Let me see. Bohr's model uses a fixed orbit theory, or like planets. Let me see. Orbit theory. We had the word shells in there, so each orbit is shells equals an orbit. I don't like that. We'll go with it. Orbits are shells. So the maximum number of electrons per shell, which is also called an orbit, is 2n squared, where n is the shell, where n equals the shell number. So if we did that, 2n squared, we would say first shell is 2 times 1 squared equals 2. So the maximum number of electrons in first shell is 2. Second shell is 2, but 2 squared. So 2 times 2 is 4 times 2 is 8. Third is 2. 3 squared is 18, and 4 squared. Thank you. 32? You wouldn't lie to me, would you? All right. And that's kind of what we need to go there. So, and it's important to note that is the maximum, but as we will look at again and have seen before, an atom does not necessarily, not an atom, I should say atoms. That makes more sense. Atoms do not necessarily fill up a ring before moving to the next. That's a poor way of saying it, but you don't necessarily fill up a ring before the next ring starts getting electrons.
Isn't that usually at the fourth ring, so that one will fill to 18 as well, and the fifth ring will start to fill?
I don't know what they normally look like. I just know a couple of them. So the outermost shell is called the valence ring, valence ring. And those electrons are called valence electrons. Because of the laws of attraction and repulsion, if you remember, opposites attract. I had all kinds of things to say. Just leave them alone. Opposites attract. So we have a negative electron floating around a positive proton. This is the interactive part. And they attract each other, so they tend to want to come in. But why don't they?
Neutron.
It's too much energy. Like a toddler on crack. Just bounce around. So, I mean, they're attracted to the parent. They just kind of, just run around you, but they don't stick to you. So, it's a very accurate analogy. And for whatever reason, the electrons don't want to stick to each other because they, again, a lot of energy, and they are both negative, so they tend to repel. I can't really explain why within the nucleus the protons and neutrons stick together. You're going to help me? Okay, go ahead.
There's a force, just strong force, and once subatomic particles get within a certain proximity to each other, it's like a polarity flips and they just stick together. But it has to take an immense amount of force to push them close enough together to stick.
Okay, but they do stick.
They do stick.
And if you could unstick them, you'd be a very wealthy person because, let me see.
Bingo, boom.
Yeah. Let me see. Number of protons in an atom determines identity. Yeah. 6 protons. If you had 6 protons, you would have.
Six neutrons.
Yeah. Okay. And 6 neutrons. But that makes up what material?
Carbon?
Oh man, this guy's good. Carbon. If we could somehow remove 3 from that, just get in there and pick out 3, we would have minus 3 equals 3. We would have
Beryllium?
gold. Yeah, if you could remove 3 protons from, oh, I'm sorry, not carbon. Lead, that's it. Lead.
Oh yeah, there's like the old turd lead into gold like
Okay.
alchemist thing.
Yeah, that's it, yeah.
Yeah.
Philosopher's Stone?
Yeah.
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 Yeah, if you can remove 3 protons from lead, I don't know why I wrote that there. Remove 3 protons from lead, which has 82. So I'm sorry, we'll just get rid of that. So we have lead has 82, because I know gold doesn't have 3. I'm like, well, that makes sense. That's like a gas. But if we can remove 3 from that, it would be 79. We would have gold. Okay, there we go.
So they want us to build a lead-based proton bomb.
Yes, lead-based proton bomb. I'm sure nobody's thought of this, except for us and the book that I read. Okay.
Which book was this?
So let's see, the number of electrons. All right. We talked about that. If the number of electrons, get out of my way, the number of electrons equals the number of protons, the atom is considered,
Mobile.
well, it's mobile if you can carry it. It's considered, is it positive? Is it negative? Neutral. Neutral. All right, so if we have an extra electron, then it is positive or negative. It's negatively charged. Ion. Or an extra proton, it's actually better to say a deficient electron, I think. I will say. Equals a positively charged ion. All right, how fast are these little suckers, these electrons?
Pretty fast.
All of the miles per hour.
Electrons move at about the speed of light. which is 186,000 miles per second. Again, like a toddler on crack. I don't advocate giving your toddlers crack, by the way. It's
Yeah, have you done this before?
You need to have a lot of experience with crack dogs.
He mainly just had to get that on recording.
I know. Sadly, I do have experience with toddlers on crack.
Oh, I understand.
What?
Huh? All right, and it's not a good thing. Let me see. Depending on how many electrons, there are in a given atom, and how they are arranged, and how they are arranged will determine if the material is an insulator or conductor. An insulator keeps you from dying. A conductor does not. So a conductor will allow movement of electrons. The movement of electrons. In other words, electricity. An insulator will prohibit the flow of electrons, or the movement. Asterisk, sort of. What's the caveat to that one?
Semiconductors.
I was thinking of something different. You're not wrong.
If you give enough power to it, it'll just go through.
You put enough voltage through an insulator, it works. It will conduct. All right, let me see, an insulator. So electrical flow. Yes? I go a little too fast. It's review, so I get bored.
Have you heard of the term, if it passes current, it passes code?
If what?
If it passes current, it passes code?
If it passes current, it passes code. Yeah, I've seen some work that makes sense like that. You good? All right. Electricity is the movement of what?
Electrons.
All right. Electricity is the movement of electrons. Is the movement of electrons from one atom to another. And the fundamental principle is attraction and repulsion. We talked about that. Unlike charges attract. Let's see. And we had talked about in 309, if we have an atom, we'll just draw a very simplistic one, so I don't have to draw here all day. And we have a bunch of electrons floating around. We have another atom. That'd be my nucleus. And we have electrons here. We have another one over here. We'll just make them like that. It's 4. Now it's a semiconductor, but pretend like I didn't say that. All right, so if we add a voltage source, and we ground this side, what happens here?
Electrons are knocking into each other.
Electrons start knocking into each other. So this is a ground, that's a ground, which means electrically it's connected. So we can just complete that so it looks better. So we have a negative here and we have a positive over here, which is to say that opposites attract. So the negative is going to want to go into the positive. And like repel. So here we have the negative side over here. So this is the negative side here. So that negative is going to want to do what to this one? Push it. And that's going to push this one. That's going to push this one. And this one's going to go, hey, look, there's a positive. I want to go over there. And that's going to go that way. And we have flow. And then the battery works because on these plates, this long plate here has a deficiency of electrons. It's a plate that's been basically stripped out of electrons, so it needs a whole bunch of them. And this positive plate is going to have more electrons, and so it's going to want to get rid of them. And what we're doing when we have a battery and we connect one side to the other is the whole battery wants to equalize. And so the electrons flow from one side to the other. Now, we know that electricity is actually going to flow this way, from negative to positive. And from negative to positive is called which theory?
Electron flow theory.
Okay, flow from negative to positive is electron flow theory. I'm going back to black for no other reason than I think it's easier to see. And flow from positive to negative is conventional. Conventional flow theory. Well, which one's correct? Well, it depends on what you mean by correct, I guess. Well, I'm the one that said it. So
Generally, you'll see more commonly the conventional theory on schematics.
schematics and the way things were drawn. So when we start looking at diodes and what's the other thing I wanted to say? Diodes and the other thing that I just, not capacitor.
Relays.
Yeah, electronic relays are called.
Solenoids.
It'll come in a second. They're written in more of a conventional theory flow transistor. If you look at transistors and you look at the way diodes are written, they seem to fit better if you just stick with a positive conventional theory. Also, when you're doing troubleshooting, like schematics, I think it's a lot easier to look at conventional. So I tend to just follow a conventional, as long as we all understand what's really happening. Not that it makes a lot of difference, other than when you go for your FA tests, you would look kind of foolish if the examiner's asking these things. You're like, oh no, it definitely goes from positive to negative. You're going to look a lot brighter if you go, oh no, it's negative to positive in the electron theory flow, but I perhaps, prefer the conventional. How would you like me to speak to you? And you're like, okay, never mind, this guy's got it. People said to me when I was testing, like, any way you want, you understand it, I'm good. So for me, troubleshooting works better positive to negative. And there was a period of time when that's just what they thought, and that's how things worked. And so, like I say, it doesn't make a lot of difference if it actually worked that way for a period of time. Like, oh, we're just backwards, but it still works.
Did you say that they did that pretty much until like the 60s or something like that?
I want to say it was like 50s, but then I could be wrong on that one.
Because the transistor was mid-40s, so it makes sense.
Okay.
They had the other theory.
Yeah, that's the way they were drawn. It's like if you fit it in a conventional theory, it's like it makes perfect sense. All right. Let me see. Electrons are therefore positive, conventional. All right, 3 types of electrical properties. We have the conductor, which passes electricity. How do we define a conductor? Atomically speaking, has less than 1/2 of allowable valence electrons. So we're getting out, and our really good conductors, which I'll write down again, we tend to get out into shells where they're starting to get further away from the mothership there in the middle, the nucleus. And so they're free to pass around, something they call free electrons. Maybe not in this case, but they'll move much easier. So we say that the outer electrons are loosely held. And I will say all of this stuff here, you might be thinking, well, why does this matter? This theory right here and how they work is going to matter when we get into semiconductors. If you can follow this, which I don't think is too complicated, you can take this model that we're talking about now and move it into semiconductors and go, oh, yeah, that makes sense, hopefully. They're loosely held, so they pass around much easier. So what are some of our popular conductors?
Gold, copper, silver.
Copper, silver, gold, aluminum.
Lead.
So copper, I didn't write that one down. Copper has 29 electrons. And if we talk about our shells, we had the allowable was 2,
8,
8.
18.
Is it 18? Yeah, 18, 30, 32. 32 is the next one. Okay, so just to keep that over here. So copper has 29 electrons arranged 2, 8, 18, and then 1. So it's way out there. Silver has 47. And that is 2, 8, 2, 8, 18.
18 again.
And then 18 again, and then 1. And then gold has 79 because lead has
8, 2.
yeah 3 more.
Be a second to add 3 to that.
What's that?
I said to be a second to add 3 to that.
Me too. I have my calculator. I just wait for somebody to yell. I'm like, yeah, that's correct. Gold has 79 electrons, and they are 2, 8, 18, 32, back to 18, then 1. And aluminum is 2, 8, and 3. So why don't we use, of these, which is the most expensive? What's the next most expensive?
Silver.
Next cheaper, I should say. What's cheaper than silver?
Copper.
Copper, then
Aluminum.
why don't we just use aluminum for wiring?
Doesn't
Which
work
weighs
very
more?
well.
Copper, aluminum.
Copper.
So copper's more expensive and it weighs more. How come we use copper in aircraft?
It's better.
Better conductor, less corrosive.
Corrosive. They tried it. They tried it in houses in the 70s. It was a big problem.
Aren't
And
all the- oh, sorry.
what's that?
Aren't all the big power lines all aluminum? The big hoggy ones that go from like LA to Northern California?
Maybe. I don't know. That I don't know. But I know that aluminum wiring in homes became a real problem in the 70s. And now if you have aluminum wiring, they have special procedures where you have to have a special lubricant and use a special
Fun.
connector to connect copper to go then to the switches because the switches aren't supposed to have the aluminum. And
Was there a problem when the aluminum would come in contact with steel and the electricity would create the oxidization and the corrosion?
yeah, I don't know if it was the steel, but aluminum definitely corrodes even on its own without the dissimilar metal. I mean, just leave it around, it just corrodes. And so we had the same thing with aircraft. The wire would get corrosive, and that creates a lot of problems with voltage drops in aircraft. We don't have quite as much power as 110 volts. We're only using 12 or 24. So, like my airplane I keep talking about, where the battery's way in the back, and it's got a wire that's got to run the whole length. That's quite a bit of a voltage drop. And if your starter's a little weak, battery's a little weak, you're not going to get it started, and it becomes a real problem.
So I thought copper corrodes pretty well too. I mean, you look like the Statue of Liberty and stuff. It's all green.
Yeah, it gets that patina finish, they call it, or something like that.
Is that only from moisture? Or
But
is
it doesn't. But
oxidation?
you don't see that
It
in
doesn't
copper
corrode.
wires.
That's what I'm wondering.
Yeah.
I think that's only from like moisture and like.
And it's just a
exposure to
surface.
oxygen.
And then it's a surface corrosion. It doesn't corrode through. This is just me thinking. I think if you left a chunk of aluminum out and a chunk of copper outside for a very long time, the aluminum is going to start to eat away, and the copper will just get that finish that starts.
Uh-huh.
So there is-
Which is why it's a finish. Yeah.
Huh?
It'll still pass a little bit through that oxidization where the aluminum might not just. It pretty much is just completely sealing itself off.
Yeah, and some stuff, unlike steel, where rust will go through the whole thing, some materials, that corrosion layer starts protecting itself.
Which is
What?
Isn't that copper?
Yeah.
That patina
I'm getting out of my element right
I
now.
know.
Similar,
So
right?
now I'm just gonna start making up stuff.
A lot of questions about this though.
Start saying yeah.
Interesting subject.
Uh-huh.
Start taking everything with a grain of salt.
Salt corrodes stuff. See? Okay. All right, insulator. Insulator. Well, then the opposite would be true. It has more than 1/2 of its valence electrons. All right, and I think all of the examples that I have for insulators are not like, chemically pure, so you can't, it's not an element. So you can't, I don't have.
Carbon, wood, carbon's part of rubber.
No, because we use carbon as resistors, so it still passes, so it's still carbon pile resistors to be exact. So I don't have the atomic makeup of it, but what are some good insulators?
Plastic.
All right, insulators. So we have, what I hear, rubber? Rubber, plastic?
PVC.
So like silica.
No.
Glass.
Silicone.
Glass. Glass is good. Silicone or silicone?
Silicone.
Cone, like the stuff in the little tubes that you, I don't know about that. Probably, yes. You can't paint over it.
Pink Panther.
Let's see. Wood. What else?
Ceramic.
Ceramic is a good one. Air. Air is an important one that we use. We depend upon that in the makeup of certain things.
Pure water.
Pure water is correct.
GI, I guess, right? Where is that?
It's pure water. It's what actually passes electricity in the water is the impurities.
So, yeah.
I know when I was in the Navy, I was a firefighter in the Navy shipboard, and somebody telling that, well, you can put water on an electrical fire as long as it's pure water. We're using freaking salt water, man. Where are you gonna get pure water?
Give it to me, sure.
Yeah.
If the ship, if the boats aren't, the planes aren't
All
fire,
right.
you push it in the ocean.
Sorry.
It's not a joke.
At the point where the material of the insulator gives off electrons, it is said to what? What is that word? Break down. Put enough voltage to something, it will then break down. And I'll talk briefly about semiconductors. We'll get into semiconductors in a different week. Semiconductor. Well, it's in between. Does it conduct? Semi. So it's between a conductor and insulator. And common ones are germanium. That's Michael Jackson's brother, if you're old enough, and silicon. Because his brother's name was Germain, yes. And silicon, and they each have 4 valence electrons. And I think that's the second shell. The second shell can have how many? 8, so it has 4. So is that more than half, or less than half, or exactly half?
Exactly.
So it falls right in between. Okay, break time.